This recording shows a sample calculation for the lab on heat engines, and I'm going to do that for the DC motor, and there's a lot of data to fill in, and most of them actually come from the video that I produced. So let's get started on this one. The first one that I want to do here is actually the energy that is being that enters the system. In this case, it's electrical energy. Of course, it says on the top heat engines. So for the steam engine and the Stirling engine, that would be actually the heat that goes in from the dry fuel, the aspid for the steam engine, and the ethanol for the Stirling engine. But here it's electrical energy going in. Okay, I measured in the video 2.99 volts, and I measured in the video 1.15 amps, and then technically I would have to wait until the batteries are used up, because that would be the total time, but of course that would take quite a long time, so I'm just using a token time of 10 minutes or 600 seconds, and this is the only time that the total time goes into the heat input or the energy input, and as it turns out, as it always goes into the work output, because now it appears twice, it actually cancels out, so it actually doesn't matter if I take 600 seconds or if I take 10 seconds. But in any case, I put it in there so we can come up with nice numbers here. Multiplying these three numbers comes out to 2060 joules rounded, or 2100 joules, either one of those numbers. Okay, 2060 joules. Then I'm going to take that 2060 joules and I'm actually going to put it right, I'm just trying to get there, just right. There we go, right there. 2060 joules. So that's the energy in. Okay, now the work output. The work output is the rotational energy of the cylindrical part that is rotating on the DC motor. And for the rotational energy, that would have to depend on how fast it rotates, what kind of shape it is. That's the moment of inertia coming up in a moment, and the mass it has. And at some point I had measured it to 107 grams, so that of course is 0.107 kilograms. And I have to convert that because everything has to be in base units, so that at the end we're going to come up with base unit for energy, the joule. It has a length of 50 millimeters, the 2 inches there, so that's 0.05 meters. Then the shape of the rotating part, that was a rod or a stick or a cylinder, and the correct equation for that one would then be the 112 times mass times length squared. So here's the 112. I'm going to copy this over here. There. Okay, and now I'm going to plug in the numbers. Again, I left these little dots here because depending on which engine you're working with, you might have to use 112, 1, or 1/2, so that's why I'm not writing it down. In any case, on the calculator, I'm going to write down now 1 over 12 times the mass, 0.107, times the length, 0.05 squared. Don't forget the square. Comes out with a really small number, 0.4 zeros, 1, 2, 3, 4, because the first 2 appears in the 5th decimal, and then 2, 2, I guess I can just call it. Not too many significant figures to be used. I guess I don't get that all on one. No, I don't get it all on one line. Okay, so the moment of inertia is 0.00022 kilograms meters squared. It's that small because the base units are relatively large, a kilogram and a meter squared, while the rotating part itself is pretty small. Okay, in the video I measured a frequency of 2000 rounds per minute. which I divide by 60 because again I have to have base units. So per second, which is the hertz. So 33 hertz. Actually, I could do that over here too on my calculator. There it is, 2000 divided by 60, 33. I don't have to be too accurate because a lot of those numbers are really just measured to two significant figures. Some of them are even just measured to one significant figure. The angular velocity is 2 pi times the frequency. That's because it's rotating 33 times per second, which means it goes through an angle of 360 degrees. But we have to use the competing angle measure of 2 pi. And you may remember that from the circumference of a circle. So it's 2 pi find it on my calculator, 2 pi times 33, and that comes out to 207 hertz. Now the rotational energy looks like the kinetic energy, which would be 1/2 mv squared. The rotational energy is 1/2 I omega squared. So it's going to be 1/2 times the 0.00022 times 207 squared, and that comes out to 0.47 joules. So when it's rotating at its fastest of 33 hertz, it has a rotational energy of 0.47 joules. The stoppage time we had measured to 3 seconds. There is the thing about the one significant figure. That was just really a rounded number, which means that the end result will also have just one significant figure. There was no point of making it any more accurate than that. Okay, with that, I'm going to calculate the power supplied, which is rotational energy, the 0.47 joules, divided by, minus 0. So that's when it stopped, of course. I just put that in there to show that, well, it stopped. And of course, that's 0, divided by the stoppage time of 3 seconds. So that's a rounded 0.16 watts. And the watt is the same as joules per second. So that means that every second 0.16 joules is supplied to keep the rod rotating. Because of inertia, you could actually turn it off and it should keep rotating, but of course it doesn't because of friction. And that's why I'm measuring that. I'm turning it off and it slows down to 0, and then I need an extra 0.16 joules per second to maintain it rotating, actually. And in that way, I calculate with the friction, I actually calculate how much work it absorbs, respectively. That's the output. And so this roundabout way then gets me the amount of work that is actually supplied to the rotating part. Okay, the total time, those are the 600 seconds, and the total energy used then would be 0.16 times 600, and that comes out to 96 joules. And now I compare 96 joules to 2060, so the work that was output to the heat, or in this case electrical energy that was input, comes out to 0.046, and I have to shift the decimal point, so it's actually 4.66, or with one significant figure, just 5% is the efficiency of the DC motor. Now what you would have to do is watch the videos for the other two engines and use the data that are given in the video and do the same calculations that I did here, coming up with the same efficiencies. Not the same, but coming up with the efficiencies for those, and also calculating the heat input. Notice that the formulas are a little bit more complicated than they are for the DC motor.